All right, so today we're going to do an example calculation of using the matrix formalism to compute or ray trace the path of a ray going through a thick lens system. And we're just going to do this as an example of how to compute the matrices. So I have a Python program running which basically just does very simple matrix calculations. And let's see what we have here. So here we have a lens which is concave and planar here. It's called a plano-concave lens. We have a biconvex lens, and there's a space between them. So let's put in some numbers and see what that actually leads to. So remember from the tutorial session, a radius of curvature like this would correspond to a negative focal length. So here we have a radius of curvature r equals, we're going to say negative 50. Okay? Right below it, or right after it rather, we have a translation. We'll have a thick lens with a distance of 10. And we better put units on here. So let's assume everything is in millimeters. And that is our thick lens. But how do we deal with this? How do we deal with this radius of curvature here? Well, the radius of curvature here, we can think of this as a flat surface or a r goes to infinity, r equals infinity, curved surface, right? So if the radius of curvature was infinitely big, then this is effectively the same as a straight line. We're then going to have a distance, and we'll say they're separated by about 10 millimeters. Okay, so they're separated by 10 millimeters, and then we have our second lens. So we're going to let this surface be a bit of a tighter focus. This will be r is equal to plus 40 millimeters. It'll also have a thickness of 10 millimeters here. And we finally, at the other side, will have an r equals 75 millimeters focus here. All right? So that's what we need to trace the ray through this system. Okay? And we're going to have an input ray. So just as an example, we could plug in anything, but let's assume we have a ray that is collimated, has alpha equals 0, and is 5 millimeters above. So the ray, as it stands here, is given by this vector here, 5, 0. Okay, and that's just before the surface. That's what the ray is initially, right? Just before the surface. So let's actually use the matrix formalism to calculate the ray at a point here, we'll call point A, right after the surface. Okay, so we're gonna trace the ray through this system. Okay, we're gonna use a few matrices along the way. We have the refraction due to a curved surface. And that matrix is given as follows, like this. And translation, it's a much simpler matrix. What happens between these 2 points or within a lens, that's merely going to be given by 1D01. Okay? And we can also combine these to make the full matrix of a thin lens. We'll do that in a second. Okay? So first of all, let's find out what happens right after this surface. So right initially at time equals 0 or distance equals 0, right before it enters the system, our ray is 5 millimeters above the axis and is at 0 angle. It's collimated. How would this point A here? Okay, so right after that, it's going to hit this refractive matrix, and we better give an actual value for these. Let's say n is equal to 1.5 for both of these lenses, and n is equal to 1 outside, basically in the air. Okay, so what does the ray look like at point A? Okay, point A, let's say RA is just equal to this matrix. And let's plug in what that is. So it's 1.5 minus 1, negative 1.5 minus 1, divided by 1.5, that's N2, because N2 is equal to Rn here, 1.5, and N1 is equal to 1 here, times, what have we left out? R, the radius of curvature, of course, negative 50. And the rest of the entries aren't so bad, 1, 0, and we have 1 over 1.5. So that's 1 divided by 1.5. We multiply that by our input, 5, 0, and that's what comes out, okay? So we can simplify this a bit. We can see that this is going to be 1, this is going to be a half divided by 0.5, so it's 1/3, negative, negative, it's going to be 1 over 150, if I am doing my math right. And this is going to be 1 over 3/2, so this is 2/3. But after that, we better start using Python to calculate it for us. So let's see what we get. We get the same height as we expect. I hope we get the same height. And we get 150 times 5, this is 1 over 30 plus 0. So whatever 1/30th is. So that is 0.0333. So it's going to have a slight angle. Which way is it going? Up or down? Well, it's going to be bending up slightly. Okay, so let's actually plug that in. So now is as good a time as any to show that we have here. So we have in this code here, we have just array, which is just a 1x2 array. We have array to string, which is just a nice way to print it out. And we have different matrices. So these are just the matrices we've drawn on the board for translation, refraction, and we can make a thick lens just combining refraction and translation matrices as we did in the lecture. Similarly, we can define a thin lens this way. Okay, so let's just run that. And we're going to say R is equal to array with height 5 and 0. And what does array to string tell us? Just make sure this works. Okay, so I'm going to modify this code just to return this string here. I don't care that it says input array. Okay, so that's what our array looks like. So after the matrix, we're going to go R times, this is the Python way of writing a matrix. So it's going to be a refraction matrix, RMAT, with radius of curvature of -50, and 1 is equal to 1, and 2 is equal to 1.5 by default. So that's basically all we need. And that's what it's going to return. So that is 5. And why don't I just print this out? Okay. So that's our new thing. We're tilted up slightly by 1.33. And so we're going to have a slight tilt of this ray. Not very much, but a little bit, pointing upwards as it goes through this surface here. The next thing we do is we can look at a separate area, point B here. Okay, so at point B, what's going on? Well, we've just had our input ray, which is now RA, and we've applied a translation there. So let's write down what it looks like at B. At B, we have a translation of distance 10, we said millimeters, so it's 110.01 times whatever's going into it, and that's going to be 5 and 1/30. Okay, so we are now going to change height. We're going to go from 5 to 5 plus 1/3, 5.33 here, and now we're at the same angle as we expect because translation does not change the angle, so we're about 1/3 of the way up. So if this is 5 units, we've only gone 1/3 of a unit up, but it is pointing up slightly. All right, so it's going to do something like this. I'm going to exaggerate it just a bit, like that. Okay. How about directly after? Directly after. Oh, by the way, we'll type this in now. So we're going to have a translation matrix of 10 times R, and we'll print it out again. And we're now at 5.33 as we predicted, and the same angle. Okay, so how about at C? How about directly after this? Well, this is the power of the matrix approach, and we're doing it slowly, but you can see how a computer can do it very quickly. We're just going to apply another matrix here. Now it's going to be a refraction matrix, R. So for point C, we're going to have a refraction matrix with N2, the transmission is equal to 1, N1 is equal to 1.5 here, N2 is, well, we already have that, and R is just infinity here. R is infinity. So it doesn't even really matter what these ones are. That's going to go to 0. Does this thing give us the identity matrix? Does it do nothing? Interestingly not. It does something. Let's figure out what it does. So we've got 1 here, 0 here. We have a 0 here, but we do not have a 0 here. Now we have 1.5 divided by 1. So it is not the refraction. In fact, it's going to change the angle. All right, so what we're going to get is the ray at point C here, I should actually label that, is equal to 1, 0, 0, 3 halves, 1.5 times whatever went into it, which was our 5.33 repeating and 0.033 repeating. Okay, and that's going to be the same height, 5.33, as we expect, because at an interface, but the angle is going to change. We're going to get 1.5 times 0.033, blah, blah, blah. Why? Well, it's Snell's law, right? This actually predicts Snell's law. We're going to have refraction going from one index to another. So let's do that. Let's plug in another refraction matrix, but we have r is infinity. Let's just say r goes to 1 times 10 to the 8. N1 is equal to 1.5 now, and N2 is equal to 1 times r, and see what we get coming out. I'm just getting Python to do all the heavy lifting for me. Oh yeah, of course. We're going to get that, won't we? 1.5 times that. So we're going to get 5.33 times 0.05. 0.05. So we're at a new angle now, slightly steeper, and that's where we get to C. How about to point D here? Going to this point in the lens, okay? Well, we just apply the translation again. At D, we're going to get our translation, which we said again was 10 millimeters, 10.01 times whatever came in here, 5.33 times 0.05. Let's just go right to Python here. We're going to go translation 10. 5.833 in the same angle, so it's gone a bit higher, not much, but a bit higher, so it's going to do something like this. If I could only draw. And we can do the same thing for the second lens. Let's skip that step though. Instead of doing each refractive surface, remember that we can combine all of our rays. We can combine all of our rays into a thick lens matrix. So if this is going to be, we're going to call this R2, and this is going to be T. We'll call this R2, this will be T, and this we'll call R1. The matrix corresponding to this is going to be R2 times T times R1, and that's going to be our thick lens, right? Now on the code here, we've already done this, okay? So we see this, we're just returning for a thick lens a refraction of R2, transmission matrix, and another refraction matrix. So we can combine that all into a thick lens. So let's do that and see what we get coming out the other side. So we'll go TL. R1 was 40. R2 was 75. And N1 and N1, what we're coming from, is 1. N is just, we have to give it that, 1.5. And we're going from air. I think that's everything we need for that. And now we're missing N. Okay, what did I do wrong? So I have R1, R2, D. I didn't tell it the distance, which is 10. All right, there we go. So we're now at a slightly lower height, 5.68, but look at this, we're now at a negative angle. So we've gone down a touch, and we can kind of see what's happening here. We're now pointing at a lower angle here, right? So now we have some negative output angle, alpha, alpha is less than 0, and we have a collimated beam going in, so we can ask the final question of how far do we have to go before this beam here, this line, crosses the z-axis. So we have alpha here, this is technically minus alpha, and we have our height, which is 5.68, let's call it h. So h is given by h over our distance, whatever that distance is, which we're going to call the focal length or the back focal length, the distance from the furthermost point in the lens system. So here we have alpha is approximately equal to h over f, minus h over f here. So f is approximately equal to minus h over alpha, and that's going to be whatever we found for alpha, whatever we found for h for alpha. So let's just print that out. Back focal length, we'll call it. And what should we call that? R00 plus R1, and annoyingly that returns an array, so this is one way to dereference it. Oh, and it's negative as well. And let's just put some units on this. We'll make it look pretty. So we'll round this to 1 unit. We'll call it millimeters. Is 93.5 millimeters. So that means that this ray here is going to go, well, if this is 30, it's going to go about 1 to 3 times. So to scale, it would be something like this. And that's what that beam would do. Similarly, if I could clear up a little space here, if we were like flipped around, mirrored around the axis, well, it's going to be the exact same thing. Okay, so it's going to do something like that. A point right through the center is going to be undeflected through the center of these lenses, and for other points we can kind of interpolate. And we can see what an arbitrary set of rays will happen, a bundle of rays, what will happen to those rays in this system. Okay, so this is the ray tracing approach. We can actually trace rays with these matrices. Now we did a lot of matrix calculations. We can actually replace this entire thing. This is the real power of the matrix approach, is we can replace this whole thing with a black box. Instead of these 2 lenses, which we know is really these 2 lenses, right? We can actually say, well, really what that is 4 numbers. I can replace this whole thing with a matrix, A, B, C, D. So what is that matrix? The first thing it hits is this thick lens. So let's just call this whole thing L1, T1, and L2. And our whole system is just going to be, well, the first thing it hits is L1. So we'll apply that to our matrix. Then it hits T1, and then it hits L2. We multiply these 3 matrices together, we're just going to get some A, B, C, D, and any input ray that comes in, we can use it to multiply it. So for example, let's just do that real quick. So I'm going to call my system matrix, M is equal to, well, let's just make a thick lens. So we'll call L2 is that. The first lens is just those 3, the refraction, the translation, and the refraction. So it's another thick lens, except R1 here is minus 50. This was a cajillion. And it has the same thickness. And T1 was just our translation matrix for 10. So we'll call our whole system matrix here, M. That's just going to be, as we said, L2 times T1 times, this is a matrix multiplication syntax here. And that's our matrix, our system matrix. Oh, times L1. And this is the matrix that I get corresponding to this entire system. This entire system of all these lenses, we could have just done this to begin with, but that would be less instructive, is just these numbers here. So it's 1.136. It is 2.19 times 10 to the 4, so it's 21.94 millimeters, right? If we look at these matrices, for example, the translation matrix, these are unitless quantities, but D here is in units of length. So down here we have negative 1.2157, so 216 times 10 to the minus 2 per millimeter. These multiplications have to work to give us the right units. And we have 0.645, the same number of significant figures. These four numbers characterize a system. This would work on any set of rays, okay? So let's actually apply it to a particular ray, the one we just used, and just to make sure we get the right answer. So let's look at our M00. That was our first one, times 5. We got 5.68. Is that right? That's what we got, isn't it? So this times plus 0, that gives us 5.68. And how about the angle? I hope it gives us negative 0.060. So that's going to be, let's just multiply it with the whole thing, times our ray, and it didn't like that because I'm multiplying with not a matrix. There we go, 0.0607. So we get the exact same answer for the ray. That's perfect. What about a totally different ray? Let's say we have a beam that's, I don't know, going downward at an angle of 0.1 radians, negative 0.1 radians, and it strikes the surface, I don't know, a distance of 2 millimeters down, just making something up. Okay, so for an example, we can have another ray that looks like this. And we can find out what happens to that just by plugging in this matrix. We have, say, negative 2 and negative 0.1. That's just a ray coming down at this angle. Okay, well, let's find out what happens to that. Negative 2, negative 0.1. That comes out down here, negative 0.04, and at a negative angle, meaning it comes down this way. So I don't know what happens in between, we can kind of guess, but it comes out this way here. We could pick another totally different ray, one that comes up at an angle of 0.2 and hits at a distance of negative 10 here. Well, that's just going to be where did I say it hit? It hit at negative 10 and came up with a positive 0.2 angle. That's going to somehow wind itself up to minus 0.6 and still have a positive angle there. So that one will, if this is 0.10, it'll be around here, coming up this way. But the whole idea now is for any, given this matrix, we've just crunched together these four numbers, we know exactly what happens to any input ray, right? And this is just a specific case when we have this collimated beam in. We can do it piece by piece, or we can just grind out the entire system matrix, abstract the details, and look at what comes out at what height and what angle for any given input ray. And that is how you use the matrix formalism.